Good morning, everyone. I hope everyone is having a wonderful day. Well, it's morning for me. It's probably afternoon for you. And let us continue discussing about IMFs. So we know that there's this IMF called dipole-dipole. It's more like a force called dipole-dipole that holds polar molecules together. But we also know that all elements have a freezing point, melting point, and the reverses, right? And let's just make sure that we have all that vocab. We know that melting is solid to liquid. And the opposite of that, obviously, is freezing, which is liquid to solid. Of course, we have boiling, which is liquid to gas. And the opposite of boiling is condensing. Which is, that should be a G. Gas to liquid. And there's actually a third state change that sometimes, or I guess technically it's a fifth state change here. It shows up on the regions like every so often, and that is called sublimation. Sublimation is solid to gas, and deposition is the opposite, which is gas to solid. And just going over the state changes, because we know that all elements have a melting point, freezing point, boiling point, condensation point, right? However, not all elements are polar. In fact, all elements in their elemental form are nonpolar molecules. So how the heck do you get solid substances from molecules that don't have dipoles, right? And talk about that. We're going to remind ourselves that in the atom, if I have a nucleus, here's my positively charged nucleus. I have not really a set orbit, but an area of highest probability of electrons. There's my area of highest probability. Actually, you know what? Let's make it like that. All right, there's my area of highest probability. Electrons are moving in the orbital. They are free to move around in any which way. And in general, when an atom is by themselves, the electrons, if you have two electrons in this orbital, those two electrons will be on the opposite sides, right? However, outside forces can change that. And we saw that with the induced dipole, where you can actually shift all these electrons. So let's look at two actually different situation with two atoms. Here's my first atom. That side. On that side, right? Here's a hydrogen atom. And let's call this time 1. So at time 1, the electrons are there, right? because the electrons are there, there's going to be a small, I guess, nothingness, a small, you can almost say, oh, I forgot to charge, a small repulsion. But here's the cool thing. We know that these electrons, especially if these two atoms are bonded, these electrons can move back and forth in these bonds, right? These electrons can, they're just kind of moving. So what if instead of them, the electrons being there, assuming, let's call this in one covalent molecule. So just to clarify, these two right here are actually bonded, right? They're bonded, so the electrons could theoretically move back and forth. It's the same atom, so they have the same electronegativity. Let's say that at state 2, the electrons are both here, right? Well, notice that at time 2, we can see that all negative charge is at one side. All the negative charge is at one side. That means that it's asymmetrical. Oh, look at that. We have formed, because all the negative charge is at one side, time 2, we have formed a temporary dipole. Right? Now, let's say the electrons keep on moving. And the electrons move both to this side. Look at that. At time 3, all negative charges are at other side, right? Formed another temporary dipole. Okay. But then at time 4, say the electrons went back to the middle. Right? We could see that 2 out of these 4 times we have temporary dipoles, which means that we have some sort of force of attraction. But it's not a permanent dipole, so it's not as strong as our dipole-dipole. It's a very dispersed force. And this happened simply because we had electrons that can move around. And this is actually a really important type of force of attraction, type of IMF. This is called dispersion forces. And these are forces of attraction from temporary dipoles. And the cool thing is that the only requirement we had was electrons, right? That means that any substance that has electrons can exhibit these dispersion forces. And in fact, everything does. All substances exhibit dispersion forces. Everything does. Okay. So if we look at let's look at 2 different molecules. Let's look at CH4. Looks like that's CClH3. All right, we know this is nonpolar. We know this is polar, which means that both of these will have dispersion forces. But only one of these is going to have dipole-dipole. That's right. So you can have both. And in fact, things do have both. Anything that has dipole-dipole has dispersion forces. Anything that has dispersion forces doesn't necessarily have anything else. You can have just dispersion forces. So let's take a look at how this affects different properties. And I'm specifically going to look at the different boiling points of our halogens, our group 17 in their elemental form, F2, Cl2, Br2, I2. And you can look all of this up on the reference table, but their boiling points are 85 Kelvin, Cl2 is 239 Kelvin, Br2 is 332 Kelvin, and I2 is 457 Kelvin, right? So when we look at these, we can see that they have different boiling points. And we can also see that I2 has the highest boiling point. It has the strongest intermolecular forces. But of course, because all of these are nonpolar, are all nonpolar, so only exhibit dispersion intermolecular forces, right? And what we can say here is that if you're only looking at dispersion forces, dispersion forces get stronger with an increased gram formula mass, which makes 100% sense because the bigger the gram formula mass, the more atoms or the more electrons actually you're going to have within your formula, right? A bigger atom will have more electrons in it to keep it neutral. Smaller atom has less electrons. And the more electrons you have, the greater the dispersion forces. That's really how dispersion forces go. Bigger mass, more dispersion forces, or bigger gram formula mass, okay? Because you have more electrons, which means a greater potential. Thank you so much for watching. I hope everyone has a wonderful rest of the day. Bye.